Go.
Hi, everyone. Welcome to Friday MLBBQ. It is the 17th, and we are going to talk a little bit about some brain harmony. Um, Today's going to be a little more freeform, as I'd love discussion from you all. If you have any questions as we go through, it would be great to sort of have that input as we talk about this. One of the big things that I did while going through this paper is really try to dissect what they're saying with all of their jargon, as this is a very jargon heavy paper. So today, really, my goal is to go through a couple different things. We'll go through the background, the data details of what they're doing, the model details, performance limitations, and discussion. And so first, I really want to highlight, like I do with every presentation, is the authors. Why are they relevant? Who are they coming from? What is necessarily important about this research in their line of research? So this is coming out of the National University of Singapore. Very prominent researchers in this field. Wan Helen Zhu. She has done quite a lot in the space in terms of looking at these diffusion models, looking at disease states, particularly with sleep, aging, and Alzheimer's disease. And so, specifically, they're trying to now fit one of the previous models that they had into more of a disease set. Um, Ji Juan Dong is the corresponding author for this paper, and specifically, this paper was submitted for NeurIPS 2025, which they did get accepted. This is based off of their 2024 NeurIPS paper, which was called Brain JEPA. And so we'll talk about that as we go into this. But just to give context, this is the most recent work that they have come out with in terms of this uh, research line. And so right now they might be ready to submit something for or getting something prepared for the summer for NeurIPS 2026, but at the moment this is the current state of the art.
Yeah, like we all should
Um,
be, right? We all should be getting it. Mm.
Absolutely, yes, that or any other machine learning conferences that might be coming down the pipeline this summer. But let's talk about this. This is a very jargon heavy paper. I have a lot of qualms with it, so as we go through, please make sure to ask questions. I have the paper pulled up as well, so if we need to get into some of the details, I'm happy to do so. But in what this main thesis is doing is it is trying to talk about brain harmony, or their term, brain harmonics, spelled with an X at the end, as their method. And it is trying to combine both the brain morphology from T1 weighted fMRI images or T weighted MRI images with functional dynamics from fMRI images into a 1D brain hub token, um, which they say that can adaptively predict downstream tasks via these attached projection heads, which we'll get into. And so, specifically, what they're doing is taking this structure, they're taking the dynamics, they're trying to put a prior of a geometric harmonic onto this, and then putting this into what they call brain hubs. And then their method, brain harmonics, comes in to help predict maybe neurodevelopment disorders, cognition, and the neurodegenerative diseases. And specifically, right off the bat, one of the first issues that I have with this paper is their overview figure has mixed fonts, which I know is a very small point, but the fact that they have more Comic Sans Brain Hub here leads me into not liking their method as much. I know it's very aesthetic, but when you start to mix some of these, it looks a little more showy than actual results. That's my first opinion here, but let's get into it. One thing that has been coming out more recently is this idea of JEPA, or Joint Embedding Predictive Architecture. Specifically, this came out, I want to say 2022, 2021. Jan LeCun and Meta really started to preach about this new idea of trying to learn an embedded latent space rather than just next token generation. And so specifically, we've been coming from many different paradigms over the last I would say 5 to 7 years now, with the introduction of GANs, or generative adversarial models, or networks, I should say. But this idea of trying to generate data from an embedding. And so specifically taking some kind of input, the output, we have an encoder going through some kind of function with an encoder and learning the latent space for a joint embedding from a couple different modalities. We can then sort of extrapolate that where we have some noise that we put in here. We're learning a decoder to try to find this space and have a better per pixel or raw generation of new features based off of our samples or even the multiple modalities that we're trying to input into our model. That's great. And so the idea then became instead of trying to actually predict the actual raw output or per pixel basis, or if we're in images, the selection or target parts of the image itself, let's learn the latent space of the actual data itself. And so we start to get a joint embedding where we have an encoder, predictor of the latent space for the encoder, where we then find some kind of function to actually get this representational basis. Now, that is not to say that this is actual performance as it is still learning the latent space and not the raw pixels. So there is issue down the road. But just like Jan LeCun, Meta, and everybody around his sphere are trying to claim this is more learning a meta representation of the world or our space in itself. They use this a lot with images, with videos, especially with iJEPA, VJEPA. I believe there's VLJEPA now, and every kind of alphabet under the sun you can add to JEPA. And so here they started to do this with brain imaging as well, with the paper in 2024 called Brain JEPA, where they were trying to take structural images and learn the latent space of those structural images from a joint embedding. And so I wanted to pause here. Are there questions for those who don't who are not quite as familiar with JEPA architecture before we jump into sort of more brain-centric data?
Yeah, but even for brain-centric, can you say in the rightmost in C, what is X, what is Y? X is structure, Y is function, or what would it be?
So this is just coming from the general JEPA paper. So here we have the predicted architectures embeddings of signal Y from a compatible signal X. So they're both different data, and they're both doing an encoder, and I believe the predictor is trying to predict the latent space of the encoder for X, and then Y is coming in here as you're trying to combine the joint latent space and learn upon that.
So those could be two different modalities, right?
Yes.
Okay.
So it could be something like uh I don't know, image and text, for example.
Yep. Thank you.
Great. And so specifically, the joint embedding is trying to find multiple modalities to a unified latent space. It is in the realm of self-supervised learning, and we have to definitely take that into consideration as we sort of go through these models. Great. So, big thing that I want to start to talk about is the data itself. And so they used quite a lot of data. And specifically, the big piece that they use is UK Biobank. And then the ABCD data set or the adolescent brain cognitive development data set, where they curated roughly 43,000 participants, were aged between 44, 83 years old. So pretty much a wider range to older development, where the ABCD data set was about 11,000 participants. And this was going to be a different age range from 8 to 11 years for their baseline. And they are still on the tens of thousands of resting state images. This is great. However, one thing you can easily notice at first is the issue of imaging parameters. Let's talk about TR. TR is a very interesting piece as this is the amount of time it takes to scan your whole brain. That means that there is going to be some kind of difference between how we get the full scan, the time point that it is at, and the duration of sort of the scan itself. And so, having different TRs, this creates quite a large challenge, especially as you cannot compare apples to apples for time point to time point. Here, this is one of the major challenges that they have, and so we'll talk about the way that they go into trying to mitigate this difference in image quality capture. And so that is one thing I want you all to keep in mind as we start to go through is this deprecation potentially of TR or the difference in data sets between this. In their data set, they specifically um, used a couple of different stages where they, after pre-training, they did use the ABCD data set and they used the UK Biobank, where they were able to downsample many of their faster data sets. So the Biobank had a TR of 0.735, so sub-second still, and they were able to downsample that specifically to 1.6 seconds, 2.4 seconds, and they ended up having something like a 250,000 resampled sets of data. And so this is heavily resampled data as they start to go as well. So on top of having a mismatch of TRs, they started to deprecate the TRs to try to better match the differences from their data as they went on. Um, in terms of testing, as we saw before with their overview image, to be able to test these, their big model here, they had a couple different data sets that they tried to do classification tests on, and that is going to be Abide, ADHD, and ADNI, which they did not even list in their diagrams in their supplementary section. But all of these are specific as they all have a varying degree of TR as well, especially as you start to get into a disease set. Deprecation is going to be quite a lot, especially as you're going to have different issues. Like ADHD is going to have a lot more head motion, so probably TR is going to have to be a lot quicker. ADNI is very interesting because the TR is absolutely slow at 3 seconds. There's all kinds of litany of issues with that as well. And they even have the HCP-A dataset or the Human Connectome Project Aging Edition, where they have a lesser, I would say it's just different types of scans in general. One thing they did not report in all of these is whether or not the participants had their eyes opened or closed. I think that is quite a big issue that they didn't report that, but I think comparing this all is okay potentially at their scale. As we go through, we can start to look at that and how they do that. Any questions on, oh, and they use the Schaefer Atlas, which is 400 parcels. So that's a huge ROI number as they're going through. Um, I heard some rumblings. Is there any questions about the data right now?
Can you hear me all right?
Yes, I can hear you now.
Great. I have a question. Why tier is important here? Is it somehow affecting the latent embeddings? Like,
Yeah, so they have a method called tape where they are padding essentially the TRs that don't actually have it. I think it's ill-informed and chock full of jargon, as one of my hesitations on this, but essentially they just pad sequences that are either too long or too short and with the down samples.
so they kind of trying to synchronize different resolutions.
Yeah, so really this is how they're doing it. They're essentially they call it TAP or they call it the temporal adaptive patch embedding. And so the tokens represent the same temporal distribution, and that's going to be tau here. The embedding weights are correspondingly resized. So shorter time series with fewer tokens are zero padded. And then they're trying to learn these additional weights with attention. Um, and then they exclude padded tokens afterwards. So it's like a stretch and then learn about it and then compress again. I think it's a little disingenuous, but that's okay. Does that help, Pavel?
think so. Did they validate this
Yeah,
approach?
because the big issue too with this paper, they have the 10 pages like NeurIPS, but when they start to go through even just this one method, they have this simple graph here, or it's just nothing to me, honestly. Where they kind of talk about, oh, it's an embedding layer, and then we do an inverse transform, and it's some kind of pseudo inverse. We're learning these weights for this embedding, and I'm kind of thinking this is a linear transformation, but they're still doing uh, bad interpolation between time points. And so even if you had like a TR point 0.8 and a TR of point 0.6, that's just not an alignment enough. Or maybe I'm wrong. Maybe they can find the difference between the two within the embedded space, but it feels like they're making up quite a lot of their data, if that makes sense.
TJ, I have a question. So this tape stuff, this is some kind of pre-processing before they actually provide this to the encoder, because from what I understand, they're using a masked autoencoder. So they're gonna mask part of the time series or something. So this pass
Yes.
occurs before that.
Yeah, so let's go back and talk about the whole model itself. So it's a unimodal encoding is what they're calling it. And so what they are doing here is they do pre-training ahead of time. And they are trying to learn the structure of the autoencoder. So they're taking this brain morphology, the 3D SFMRI, and they're trying to do an autoencoder here where they have the encoder and then the decoder stage where they're predicting sort of this structure, and that is what they're calling brain harmonics S. Um, in the same vein, they have a brain harmonics F, which is their functional embedding. And so what they're doing here is they have some kind of padding, which they're doing here. They're trying to do an attentional weight to learn this downsampled data. So basically, they're taking their data, shrinking it down, and then learning the in-between factors of them between both ABCD and UK Biobank. And then once they're able to do that, they're doing this encoder via a geometric harmonics. Now, this is where it gets very important as they're doing a, what do they call it? Um, Laplace, it's a specific learning. I apologize. Where's the word? I should have highlighted this. But essentially, they're doing a Laplace transform based off of the structure of continuous space. So it's basically learning the structure of a sphere, or in this case, they're doing cortical structure. And so here they're trying to find the eigenmodes of this data structure to put a prior on even the functional states.
So this prior is shared somehow between the functional and the structural data.
Yes, kind of. So what I believe is that the brain morphology is still an encoder and decoder, where they're still trying to find those. They haven't even gotten to the harmony or they call it the harmony transform, which we haven't even talked about here yet. But they're basically doing two different models of the brain harmonics S and the brain harmonics F, which are should have a line here, but these two are separate from each other right now. Um, Sorry, I just saw the hand.
Yeah, I had a question. So these data for fMRI, are they raw recordings or pre-processed or ICAs?
Yeah, so we're going to assume that they're pre-processed. There is a rabbit hole of papers I was trying to go into as well. They do not give the pre-processed constraints within the paper or appendix, and even in BrainJEPA, they don't do this as well. They just kind of say this was done previously, yada yada, as many papers do. But I believe we have to take that their pre-processing is going to be okay, especially because they're using tens of thousands of subjects and imaging.
Do they provide code so we can look?
I believe they do. It's ambiguous. I mean, they have the checklist from NeurIPS that says that the code and model weights are provided. I did not go into a GitHub or try to track that down yet. So I apologize for not having that.
Yeah, thank you. Good to know. Thank you.
Yeah. Big thing here is I don't know if they took out global signal or not. I know that's such a divisive thing to do. So it could be in there, it could not be in there. Depending on how they do their geometric harmonics, really they're taking out. This came from a paper in 2024 claiming that there are harmonics functionally that can be decomposed to in about five different states. It sounds very similar to stuff I'm sure everybody in here knows about in terms of both caps, QPPs. We can talk about wavelets. We can talk about different kind of bases, but it sounds very similar to all of that. They're just giving it a different name and trying to say it's some kind of geometric harmonic on the Riemann on a Riemann surface. And so essentially they're just taking the first five eigenmodes of the geometry based off of a cortical structure. Um, okay, so now that we've gone through sort of that. Oh, it was Laplace Beltrami operator. Um, and it's just trying to go past having an ROI by ROI graph and rather look at the dynamics of how the function moves across a surface. And so they were looking to more find the yeah, just the ordered frequencies and it there's just a lot of jargon within it. But essentially they're just finding different modes that are captured by the brain dynamics with large data and then trying to use that as their bases for the brain harmonics F specifically. Okay. So as we keep going, again, tape is just what we were talking about. This is a very serious issue in my mind. I am a little frustrated by the claims that they made in this paper saying that this is one of the first, or this is the first time that someone has tried to mesh different TRs into a model. I thought that should have been flagged more by the reviewers looking at open review, but it wasn't, and I think that's fine because it was just buried in jargon, but uh, yeah, they're essentially just trying to interpolate on downsampled functions and calling it temporal adaptive patch embedding. Okay. So they're extrapolating on a lot of data and trying to find a way to not just go by time point, but they have an embedding here to use for their construction. Okay, so if we believe that and we can assume that their TRs are all matching now, that's great. We can start to look at their multimodal fusion. And so this is really looking at how they get to a learnable 1D brain hub token. Um, and so specifically, I was going to take the math in that, but we can just go through this briefly. Um, a lot of this is just trying to get the latents to talk to each other. There's a lot of little variables in here, but if we look at the structural and the functional sort of basis that they are getting for the latents, they're just trying to pair brain harmonics S and brain harmonics F, where they have a common D embedding. And so that goes back to how they're trying to make a 1D vector for each of these pair embeddings. And so there's a lot of math here. They're calling it a or a harmonizer transformer, where they're essentially just taking the joint embedding of the two and finding some D number of inputs where they can have these hub tokens updated to their basis H. It's self-attention, so they train it on quite a lot of data as they're passing it through. And they claim that having both this structural and functional token can then be then encodes both modalities, which is why they call it a multimodal embedding. Here they are minimizing over the different bases. So the harmonizer one, the structural and functional represents everything, and they take the mean squared error. And so they're just trying to find how these bases will represent themselves as they input more and more data. Oh, hello. Great. Are there any questions sort of on the multimodal fusion part? I know it's a little it feels slightly disingenuous to say 1D tokens, but I get what they're saying and they're trying to represent it in the same language as LLMs right now.
So to get it right, they somehow merge these two embeddings between modalities and
Yes.
then train the decoders to reconstruct the original modalities, the original embeddings from this merged modality.
Yes.
Okay.
Yeah, and they're treating them both as a linear combination of the two in their loss function.
Okay, thanks.
Yeah. Great. So at this point, this is pretty much all they've given us in the paper, and then they are saying, let's look at some results. And so there's a lot of numbers here. I'll try to help navigate a little bit more. What they were trying to do is keep more structure-based models and function-based models separated from each other, and then put their own as a multimodal model. And so here specifically, they have the morphology, if that's captured, the dynamics, if that's captured, and then multi-TR, if that's captured. I still have quite a lot of qualms, but what they're doing for testing wise is to see if they can discern between multiple diseases at once. And so we have Abide and Abide 2, which are specifically autism spectrum disorder data sets, and ADHD, which is going to be attention deficit, ADHD, attention deficit hyper something disorder. I'm forgetting. I apologize, guys. Yes, thank you. And so basically trying to do classification on those, and they do highlight that they're not the best all the time, and their accuracy versus F1 is all over the place, it seems like, but they're trying to highlight that their model is on par with other models that have come out in the last 2 to 3 years. Biggest thing that I wanted to highlight is that even with, I don't know, ADNI, they're still underperforming what I did even 2 weeks ago, last week, with a simple random forest classifier. Um, I I'm hesitant about these results. I think they're fine in terms of comparing other generative and or JEPA based style kinds of models where they're looking at different embedding spaces. But even if we look at like BrainGAN, which I believe came out 3, 4 years ago now, whenever Goodfellow had published his stuff, it was about 2 years after that this one came out. Still getting relatively by chance for the classification differences between these binaries, specifically learning models. The performance is not even above 80%, which I have a lot of qualms with, and especially as like a base for a lot of things that we do with learning models. But their performance is incrementally better. Cool. Yeah, and even then with the neurodegenerative diseases here, we have just aging, we have Alzheimer's, and then we have Parkinson's here. Still very much similar to performance that I've seen before, even stuff that I've done this semester. And they're just claiming that it has quite a lot of benefits otherwise. But um, regardless of that, one thing that they did do that I thought was more interesting, where they did scale across different number of 1D tokens that they defined in their vector. So that D that we were talking about for their bases, how many uh, essentially points that they have to have a true embedding of the latent space and then used for classification downstream. And so if their D was 32 versus 256, the performance really didn't climb very much from 128 tokens to 256. And these graphs are quite terrible, in my opinion, especially because we talk about sort of scaling and representation of accuracy. I think this shows nothing. Since it is going from 60 to 68% or even 65 to 72. These are on the same axes between each other, and they're not going from 0 to 100. They're not going from 50 to 100. They're not even going on the same scale here. So why are they on the same axes? I think this is one of the worst graphs I've seen in a while. Trying to explain the just the number of tokens in a progressively incrementally better way. But I mean, they show a strong linear connection here from 69.05 to 70.09. That should be a straight line. Um, or even 70 to 70. That should be the same number, and they're still showing a positive correlation. So regardless of if they are actually doing correct ablation, these models do not significantly improve when adding more tokens to your embedding space when trying to do your harmonizer transform. Um, but specifically to, they also tried to do an ablation study here where they augmented the data, or they had pre-alignment or without pre-alignment, meaning do they actually use all of the data ahead of time to train their geodesic modeling embedding of the Laplacian Bell-Riemann operator. And again, performance is pretty bad. Especially when you compare the error bars with each other, they don't show significance between the
Wait,
two.
wait, can you explain why, like, this is not a binary classification, right? Or is it?
I believe it's a binary classification. They're using their model to predict whether or not it's going to be specifically with a bed to autism versus non-autism in terms of a diagnostic.
Oh, so it's a binary, okay. And accuracy, not
Yeah.
like F1 score or anything. But also, so brain harmonics without pre-alignment looks like standard errors don't overlap, right? And brain harmonics uh, on the right for the purple line say there is an improvement, right? Or I mean,
Yeah,
not
there
improvement. Not
is.
improvement is a statistical difference, statistically significant difference, probably, right?
Yeah, and I think that's probably where they get the most benefit here. Um, I do think the pre-alignment does help this model, but I mean, by how much? 4% in this massive amount of study, that's fine. But that's still cherry picking. They did only cherry pick Abide 2 to show, and then they also showed ADHD 200.
Yeah, there is
They
no
did not
difference.
show
Okay,
ADNI. They
ADHD
did not
200,
show.
nothing changes, right?
Nothing changes. No, and they didn't show Alzheimer's disease. They didn't show Parkinson's disease. If they have all of this data here and they're just cherry picking two out of the, I think, six different like studies they wanted to do, kind of disingenuous as well.
Well, just to be a sort of author's advocate, um, like they're doing cross-validation and everything. If the model is huge, maybe the training time and university compute resources, like they maybe, so I don't know what they're really saying, but I'm with you on like rigor, but maybe that was their reasoning,
So
it's just taking too long.
Yeah, maybe I'm jumping ahead a little bit too much and putting my uh bias against this, but they did train on, I believe, uh eight H100 GPUs. And so these are really expensive GPUs, and I know this is coming out of the National Institute of Singapore, so they have a lot of money. And my guess is that being such a prominent researcher, Zhou had all of these resources already allocated to their lab. It's something like $200,000 or $400,000, even for setup and to be able to turnkey just to start on any of these GPUs. So the fact that they trained on eight of them is quite a lot of resource compute. So I agree with you, Sergey. I think it definitely had to probably do with time and just amount of training. Um, I would be curious if they had an estimate on how much money they actually would have spent on compute if they didn't have access to these eight GPUs. Um, but yeah, it is quite heavy duty to get these results that compare even worse to something I would do with like a small MDP or a small multi-layer perceptron or even a random forest classifier, which I've been able to get this kind of performance before on many of these data sets with those non-SOTA models, if you would. But
We even
um,
published a paper, Pavel sitting there on that.
yeah, yeah. Um, But last kind of thing that I wanted to talk about is they did end up taking each of their models from BrainJEPA and the Brain Harmonics F, and they tried to do a T-SNE test where they were looking more at the number of models or parameters that they were looking at. Um, Only significance here is that they had 400 ROIs, each represented by a 768 dimensional embedding. And so this huge matrices of data, they applied T-SNE, which is T stochastic neighbor embeddings, which is just a nonlinear way of trying to project these embeddings onto a 2D plane. And so this is really uh, where they can try to see the difference between BrainJEPA and the Brain Harmonics F specifically. And they claim to have significantly correlated modes at a significant level. So it feels like p hacking, but they put this in here anyway. That's okay. The connotation that they do make is their average correlation when fitted with the participant, when refactored with participants' age and the data set itself. It didn't get great correlation, and it is only subtly better than BrainJEPA, but they put this in here at the end. Um, and so yeah, really they talk about this in the discussion that the identifying bridge tokens that they were looking at captured interactions involving the default mode network, limbic network, and then cortical networks were really impaired in integration for some of the sensio-motor, the visual, or even higher order processes. And so they were really looking at how these specific embeddings were targeting the different models. But of course, we can definitely say that as you have disease, in then looking at gross structures, you're going to have issues with the default versus somatic sensor, or even visual versus the default mode network as well, or even this dichotomy of task positive versus task negative. And so that was nothing new, but it's great that they had mentioned something more neurobiologically related as well. But limitation wise, yeah, they're still messing with TR, which is hard to do. I think it's hard to find those differences with it. I know there's a neuron paper that I could probably go through a little bit more. It's called Geodesic Distances of the Brain. And I think it was published in 2024. I probably need to go look at that a little bit more. But they also claim to have these eigen modes of the brain that might have better embedding, but it's just another way to represent different states of the brain that are then used for classification on large data sets. Those are the big limitations that I see. Um, but they they see this as a way to have sort of this structure and function together. My another gripe that I potentially have is that to get to the ability to look at functional or resting state fMRI images or even task-based fMRI images, you have to map these back to structural images. I know structural images have different fidelity, they have different parameters that are captured, but they're still used as the basis for most fMRI to even align. And so I have slight issue saying this is multimodal, whereas if you had something like an EEG, an MEG, or even a completely different modality in itself, even looking at blinking and eyes or where eyes are even located, I would call that a stronger multimodal setting than just having structural and functional uh, images used for a classification problem. But that just might be a gripe from a little over promising of their results. Um, but I know we have about 14 minutes left. I think I'm doing good on time. It is a relatively short paper after that. And I did want to bring it more to a discussion if there are questions, thoughts, comments, issues, but I'll throw it all back to you if there anything like that.
EJ, do you understand the motivation for why they're using this cortical surface? Because isn't like fMRIs more like subcortical stuff? I was a bit confused as to why they were doing this and how they were actually capturing that cortical information.
Yes, so this definitely comes back to um, the this comes back to TAP. So it's temporal adaptive patch embedding, and the reason why they wanted to use the cortex is because they are able to do a Laplace um like eigenmode transform essentially because they're assuming that it's a smooth surface on which the gradient is operating on. They've done work or there's previous work done with I believe the it was Laplace Bell-Riemann operator. And specifically that is done on a Riemann surface where it is essentially smooth or you can base if you had like a plane traveling around the globe if you can calculate the distance from one point to the other point to the other point, you have a sort of direction, dynamics, and I think you can calculate a couple other features based off of just having a geometric prior. And so what they're doing with the Laplacian Bell-Riemann operator is they're essentially saying the cortex is smooth. We know that the gradients are going to be geodesically linked to something, and we can arbitrarily find these eigenmodes based off of the gradients happening within the cortex. My guess is they stayed to the cortex, especially because of the paper from 2024 on geodesic distances of the brain modes. And it probably is a lot easier to do cortex-based um, derivatives and just because you have less signal to noise as you get to deeper structures. So it's less of a graph theory piece and more of trying to find bases to this smooth surface.
Okay, is it kind of related to how they're doing the positional embeddings in their encoder for the fMRIs?
Yeah. So with the positional embeddings, um, it was more of a classic encoder decoder morphology of just trying to find what is in what's brain space or what's important here, and then finding out what is not important. So it's still just masking the images rather than even using an ROI or actually they are using the Schaefer ROI, so they are even not even doing a pixel level. Out of these 400 ROI nodes, they're just trying to find what's important, how to decode that and code that. Does that make sense? Maybe I can look up a little bit more. I
Yeah, I
apologize.
think it's, yeah, it helped your explanation.
Yeah, so just looking from T1 structured images, they're using a masked audio encoder. And so Yeah, I mean they're just giving abstract pictures, but essentially it's just an autoencoder trying to find the structure and what's relevant.
And so each modality has its own pre-trained encoder that it uses in the multimodal model.
Yes. Sorry, no, that is not true. In the pre-training, they are only using UK Biobank, which is patients 44 to 83, and the ABCD data set, which initial scans, I believe, are 8 to 11 and probably stay under 20 for all of the scans, even if they're doing longitudinal scans as well. Not mentioned in the paper for their data, but essentially they're missing out on the 20 to 30-ish state that even HEP would capture. But since they're only pre-training on those two data sets, they're using those as their basis to then differentiate with the disease models downstream.
And is this model only for classification, or can it do some kind of like forecasting or modeling of time series data?
Yeah, right now it is only looking like they reported classification. Um, Trying to do like multimodal latent space embedding to predict many different neuropsychiatric or neurodegeneration um, diseases. But my understanding is they're not even looking potentially at the differences between them or not. All they have in their discussion is there's issues with the default mode network. There's connections with limbic system. They have issues with spatio or sensio-motor and visual networks is the results that they have in like a half paragraph. So plenty of future work here. They're trying to claim an AI-driven brain digital twin, but that's also another jargon-filled thing that they'll probably get away with in another submission. But yeah, not to say that I don't have a lot of issues with this, but it's fine. Great questions. Anything else? I know we still have about 5, 7 minutes left.
Well, maybe thanks for the presentation as usual, very good and energetic. But the whole thing about foundation models or like this, what are we trying to do? If we're trying, as you said, if we're trying to build a better classifier, well, logistic regression does the thing, unfortunately, right? Or maybe fortunately.
Yeah.
But can you comment in general from their motivational and all of they compare with tons of models, but they compare them on binary classification, which is like, hey, well, we know we can do that with
Yes.
better results often. So maybe there is another more, so to say, noble reason of building models like that, right? Do they talk about it at all?
Yeah, so they make a lot of claims, honestly, and they say that they're the first to do a 1D token representation of both spatial and temporal data
Yeah, yes,
embeddings. And
but
I'm like,
why?
because they can. I think
Yeah, yeah, exactly.
it's
That
it
doesn't
for
sound like
me. Yeah,
the.
it's just buzzwords that they try to put together, and it sounded like not to bash the student or different things, as I know this is probably coming from the PI, but this is incremental work using something that is a fun new toy that came out maybe 2 years prior. Um,
But
but
if look at the table, can you roll back to the
yes,
table?
yes, 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 yes.
It's like there are. My question is not specifically about this paper. My question is about how do people motivate? Yeah, that table, like brain net TF, brain gen, and well, like what brain LM. Why do we
I
need those models besides
so
classification?
Yeah, the goal is to it goes back to Gato or the general agent
Mhm.
tokenization optimization. This is Google's model from I think 2001.
Which
It's the
you also
idea.
presented, and people who are listening to us, search in this channel and you will find the presentation on Gato.
Yeah, so it's this idea of paradigm of not being able to just do a one-to-one classification and then have an ensemble of everything. They want to have a universal model. It's a generalist agent trying to escape more of this idea of shallow machine learning to a more generalist machine learning. But more often than not, it just comes back to being shallow. They're trying to find sort of this idea that I was talking about at the beginning with JEPA, Jan LeCun, Meta. They want to get this world model. What does it mean to have structure, maybe physics, some kind of dynamics, maybe priors or something silly like that, where they can learn better actions in sort of a space. And so this idea of like self-supervised learning, the latent space of everything, they're just trying to find what is essentially in bad term a digital twin of our brain, so then we can classify what is normal, what is disease state, what is in a spectrum of something. And so they're still using this brain harmonics or the harm or harmonizer transform to use as our basis to then predict Alzheimer's, Parkinson's, ADHD, autism, um, with the same sort of latent basis.
Without
Um,
fine tuning?
without fine tuning. I agree. And it's doing fine, but it's still not even beating the normal models that we would have. Like, yeah, I think I even used maybe a three-layer multi-layer perceptron with like minimal nodes and was able to get an accuracy of 75% or something on quite a large data set for ADNI. And here they're just still even getting 64% with just their accuracy. F1 is fine, but how many misses did they have in there? Slash, are they using repeated scans? Are they having any leakage with their data? They're not even saying that the splits that they're doing. Um, I do have a lot of questions with this, and I
Yeah,
think the
yeah, but they
biggest.
don't do fine tuning, and like the goal is not classification. The goal is this, as you said, if the goal is world model, have they demonstrated anything like counterfactual or something like what do you do with this, and how do we know that we have the or the model has that model, right? Or
Mhm.
classification is the only way to confirm that it's doing something.
Yeah, so I agree with you, Sergey. I think that is exactly what they're doing. They decided to just run this method and make the basis. Then they had available these 4 to 5 different modalities for binary classification and then saw what it did and then reported on it. It wasn't necessarily they were able to say this is a digital brain twin or we used all the data we could to figure this out and now we have something else. I think they just gave cheeky names to a highly cited conference and ran with all the jargon in the last couple of years.
Yeah, yeah, yeah. You're so direct. Okay.
No,
But
maybe I can be softer. It's important still. Like
yeah,
they're
yeah,
still
it's
trying.
interesting. But yeah. People, do you
Yeah.
have any
So
questions before we wrap up for today? I don't want to take up the entire time. People in the room, people online.
thank you all for the questions, though. It's always engaging to have a couple of clarifying. Been looking at the paper for too many hours now, so it's always good to clear up some confusion.
Yeah. Okay. Well, thanks everyone for coming, and people at the center. Enjoy the research day, and yeah. See you later. Bye bye.
Great. Thanks, everyone.
Yeah. Thanks, TJ.
Yeah.